Hi there, welcome to this video on transaction management. In this video, we'll look at what is transaction management. We'll look at a simple example and understand what transaction management really means. There are different things that are important for a transaction. Those are called asset properties. We'll look at what asset properties are, and also we'll discuss in detail what are the different kinds of problems that exist when you don't implement transaction management properly, and how do you choose between the various isolation levels. All this seems complicated. Don't worry, we'll get started with simple examples. We'll understand what transaction management is first. I have let's say I have a savings account and I have a checkings account. So let's say I have a savings account and a checkings account, and I would want to transfer some amount of money from my savings account to the checkings account. So let's say I'm a poor guy, so probably I have $100, and let's say the balance in my checking account is like 200 euros. Okay, let's make it 1000 here. Savings account and checkings account has a checking account. Oops. My checking account has a balance of 200. So if I want to transfer $100 from my savings account to the checkings account, the expected output would be that I would need to have 900 here and 300 here. That's the expected thing, but usually this is not done in a single step. So when I write a program for this would be done in two steps. Step 1 would be to remove 100 from savings account, and step 2 would be to add the amount into the checkings account. So add 100 into checking account. So step 1, step 2. So what would be the result after step 1? So 1000 minus 100 would be 900, and checking account would remain at 200, and now I would need to add 100 to the checking account, so 300. So these would be the two steps that I can think of when I'm writing a small program to do this. At the end of the step 2, my $100 is transferred from a savings account into the checking account. Okay, so this is when everything is fine. Let's assume a scenario where I'm running the program and the step 2 failed. So while the program was trying to increase the 200 to 300, let's say this failed and this update did not happen. So let's say step 2, the update failed. So this update actually failed. If the program doesn't do anything and just comes out, then the state of the system is I have $100 is removed from my savings account, but it's not credited to the checkings account. So step 1 succeeded. So this was a success. So my savings account is $100 less, but the second step failed. So the amount is not credited into the checking account. So the current state of the system is my savings account has 900 and checkings account has 200, a sum of 1100. Whereas earlier I had 1200 euros, sorry, $200. So basically this means I have lost $100 because there's some problem with the program which did the transfer. And this is exactly what transaction management tries to avoid. So transaction management, when we talk about these two things form a single transaction. So whenever I talk about a transaction, everything should either succeed or everything should be failed, or basically speaking, all steps should be successful or none of the steps should be successful. That's one of the primary aims of transaction management. And what happens here is if this particular step failed, what should happen is the change which is done by step 2 should be rolled back. So this change should be removed, and the savings account should be made back to 1000, so that when step 2 failed, whatever update which was done by step 1 should be reversed so that the system is in original state. So system goes back to the state where it was originally. So the savings account has 1000 and checkings account has 200. So there is no change. At least the system is in a consistent state. So that's transaction management. Transaction management is basically identifying what are the different steps that are present in a system and making sure that either all the steps are together successful or together like if any of the steps fail, you make sure that the changes done by the earlier steps are reversed. So that's basically what transaction management is. I mean, it's kind of a very simple definition. I mean, there is a lot more to transaction management than this, but as a simple definition of transaction management, we can start off with this. So now that we understand what transaction management is, we'll look at a couple of important things related to transaction management. So there are few properties which are important for transaction management. Those properties are called ACID properties. So ACID properties, the first ACID property for transaction management, A, stands for atomicity. Atomicity is what we basically looked at in the previous example. Either a transaction should be completely successful or it should not be successful. I mean, it should not make any change. So either step 1 and step 2 should be successful together, or they should not be, or the program should leave the change. Like if any of them fail, all the changes done by the previous steps should be reversed. This is called atomicity. Atomicity is also called all or none. So basically either all steps are successful or no steps are successful. So either all steps are successful or no change is done on the system. This is basically what is called atomicity. So in when we talk about transactions, and if there are 5 steps, we call the transaction atomic if either all 5 succeed or none of them succeed when one of them fails. So that's basically what atomicity means. So atomicity is one of the main characteristics. That's A. The next characteristics of a good transaction management system is C, that is consistency. C stands for consistency. So if we look at this particular thing, the amount in this particular account, I mean in this total sum of my account before the transfer was 1200, and if let's say the system, if step 2 failed and step 1 was not reversed, then my balance would have been 1100, whereas earlier it was 1200. So basically 100 was lost. So this is basically an inconsistent state. So whenever I do a transfer, one of the consistency checks is that the amount, I mean sum of amounts before the transfer should be equal to the sum of amounts after the transfer. So that's consistency. Consistency is basically leave the system in a good state. It should not be in a state where you have to do, I mean something is not consistent. So that's basically the C. C is consistency. I is isolation. So let's say there are 2 transactions, T1 and T2, and T1 has 2 steps and T2 has 2 steps. What isolation says is that if T1 and T2 are executed in parallel, if T1 and T2 are executed in parallel, both of them together, so one step of T1, another step of T2, another step of T1, and another step of T2. So even if they are executed in parallel, the results should be same as they being executed in sequence. So let's say there's a T1 step 1 and T2 step 2 step 1 and T1 step 2 and T2 step 2. So this is the way these transactions were executed. Let's say this is how, because in a multi-threaded system your transactions can be executed in parallel, and that's what happens here. So the step 1 of T1 is executed first, step 1 of T2 is executed next, step 2 of T1 is executed next, and step 2 of T2 is executed next. So in this scenario, the result should be same as having this kind of a sequence as well. So T1 and T2, and step 1, step 2, step 1, step 2. So either if they are executed this way or they are executed this way, the result should be the same. So that basically means if T1 is executed in parallel with 100 other transactions, the output of it should not be any different from executing T1 on its own. So whether T1 is a transaction is executed with a lot of other transactions or by itself, the result should be the same. However, there are different isolation levels and there is a little bit of complexity to it. We'll discuss that complexity when we get to isolation levels. For now, isolation, you can think of it as if a transaction is executed in parallel or serial, it should have the same result. That's basically what isolation is. And the last step, the last thing in the ACID transaction. So we talked about atomicity, A, that either a transaction should be successful or no step should be successful. Second is C, consistency. A transaction should leave the system in a consistent state. It should not leave the system in a state where I have lost something. I is isolation. Transaction, like whether a transaction is executed along with 100 transactions in parallel or it's executed on its own, the result should be the same. And the last one is D, which is called durability. That basically means if, let's say, this transaction succeeded, let's say this is succeeded and my balance was incremented to 300. So now, so this change is done. So the change is done. Once the change is done, even if this system crashes, if let's say the bank, if the bank database crashed after this, so when it's recovered, the values which were changed by the transaction should be persisted. That is what is called durability. So even if the system crashes or something wrong happens, whatever changes we have done in a transaction should be saved completely. So that's basically what is called durability. So now we looked at the four different properties which are related to a transaction. So these ACID properties are very important: atomicity, consistency, isolation, and durability. So these are the important things that are related to a transaction. Let's now consider the different problems that can happen if transaction management is not properly implemented. The first one which we would talk about is something called dirty read. Dirty read is when you read something which is in an inconsistent state. So it sounds very tricky, so let's make it easy. I have a transaction A and a transaction B. Transaction A is my friend is transferring some amount to me, and transaction B is my friend's colleague is transferring some amount to him. So A is my friend is transferring $5,000 to me, and transaction B is my friend's colleague is transferring $1,000 to him. So these are the sub steps, if I can call them. So in the transaction A, step 1 is my friend's account is deducted by 5,000 and I would be credited with that. And transaction B, step 1 is my friend's colleague is deducted by 1,000 and my friend is given those $1,000. So if everything happens properly, and here I am assuming those transactions run in sequence. So so first transaction A is run and then transaction B is run. So in this kind of a situation, so this 1,000 here, the first step is my friend's account is debited by 5,000 is removed from his account, so 5,000 is debited. So now he has 10,000, so 15,000 becomes 10,000, and the next step is my account gets credited with that, so I get 15,000. And then the transaction B happens where my friend's colleague's account is deducted by 1,000, and then this should have been 10,000, and then my friend's account is given those 1,000, so 10,000 becomes 11,000. So this is what you would expect. So if the end result should be something of this kind. Let's just reverse these steps. So let's say these two transactions happened in parallel. Just when my friend was trying to transfer the amount to me, my friend's colleague was also transferring to him. and the system which is executing the transaction executed it in this way. So let's assume the order was a little different, and the way it was executed is transaction A, my friend's account was debited by 5,000 rupees first, and then the first step of the transaction B is executed, and then the second step of transaction B is executed, and only after that the last step of the transaction A is executed. So let's say the order in which it was executed was changed. Because these were running in parallel, they can get executed in any way. So in that scenario, what would happen? So my account has 10,000 rupees, so no change. The only change would be in my friend's account, so that would become 10,000. So 15,000 would become 10,000, and my account would have the same amount, and his colleague is not even involved in transaction A, so it would remain the same. However, now step 1 of the transaction B is executed, friend's colleague amount is deducted, so 20,000 becomes 19,000. However, the remaining amounts, my account and my friend's account, would remain the same because there's no change to that. And the step 2 of the transaction account increments the friend's account by 11,000. So if you see this particular change, this change from 15,000 to 10,000 of my friend's account is done by transaction A. This transaction A is still not complete. There are steps remaining for that particular transaction. It's not really complete. If this step fails, probably this step would be rolled back. There are a lot of things that can happen. But what is happening is this particular transaction is reading this value. Transaction B is reading the value of my friend's account, which is actually stored by transaction A, and it's trying to update it to 11,000. And this is what is called a dirty read. That's basically the transaction A has updated my friend's account balance to 10,000. However, it's not still complete. I have not really got the 5,000 from which needs to be transferred from my friend's account to my account. So in that sense, transaction A is not really complete. Transaction A is still executing. Only the first step is executed. Even while the first step of the transaction is executing, transaction B has already read the value. So transaction B has read that my friend's account balance is 10,000 and it incremented it to 11,000. But the transaction A has, let's say this particular step fails. So transaction A step 2 fails. What would happen is the account balance, so transaction A, it knows that my friend's account balance before the thing was 15,000. So what it does is, because the transaction step 2 failed, it would reverse the change done by step 1. So my friend's account balance would be, if this fails, my friend's account balance would be put back to 15,000. So there is a chance that the 1,000 euros which his friend has transferred to him are lost. So this is what is called a dirty read. Dirty read is happening when a transaction reads a value. This transaction B is reading a value which is updated by another transaction which has not yet completed. So transaction A is not yet completed. It still has certain steps to complete, but transaction B is already reading the value for that particular thing. This is called a dirty read. So how do we prevent this? We would do something called locking. So once this transaction A has updated my friend's account, so this particular transaction has updated my friend's account, so what it does is it has some kind of a lock. So it holds some kind of a lock. So what happens is, this transaction B, when it's trying to get the data from my friend's account, the program says, wait, there's another transaction which is using your friend's account, so don't do anything with it, wait for it. So what happens is, transaction B keeps waiting, and transaction A comes to the next step, and I would be given 15,000, and now this transaction A is completed, so the lock is released. So this lock which was held on the friend's account, and also the lock which is held on my account, will be released, and then transaction B can go and do whatever it wants with my friend's account. So the problem which we saw here is called a dirty read. So dirty read happens when a transaction reads some value which is updated by another transaction which is in progress. So dirty reads are very bad, because if the other transaction terminates, or if it does a rollback, whatever value the new transaction reads, it's outdated. So that is basically called a dirty read. The next problem which we typically face in transaction management is called non-repeatable read. Non-repeatable read is basically a same transaction. In the same transaction, you read the same value twice and you get two different values. That's basically what is called a non-repeatable read. Let's consider an example. Let's say there is this table with ID, name, age, and there's a particular row in there which is highlighted here. So let's say in a transaction, the first step was select start from users where ID is equal to 1. So this row is returned. So it sees an age of 34, my name, and an ID. And let's say there is another transaction which is happening in parallel. So in parallel with T1, there's another transaction which is running T2, and it updates the user to 21. So it updates my age to 21. Thank you. Yeah. So this read a value 34. So when this row was read, the value of age was 34. Let's say transaction 1 is running, and one of its future steps may not be step 2, maybe step 3, step 4. It's again doing the query on select start from users where ID is equal to 1. It would get back the new value. So the age which it would get would be 21. So the same query, when run at different times, it's giving it different results. So that's basically what the non-repeatable read problem is. So when inside a transaction, if you read the same value, I mean execute the same query or try to read a same thing in two different places, you're expecting to get the same value back. If you don't get the same value back because some other transaction has updated that particular value, then that's what is called a non-repeatable read. So a non-repeatable read is usually quite a challenging problem, because it means that once like if in the same transaction you read it 2 times, you get 2 different values, and there's a chance that the program will not know what to do or how to handle it. So that's basically what is called a non-repeatable read. The next problem that we are going to talk about with relation with transaction management is phantom reads. What is a phantom read? Let's consider this example. So I'm just taking a particular row in a table. There is a table with one row, and a particular transaction is executing these queries. Select start from users where age between 10 and 30. So number of rows returned here would be 1. So one row is returned back because there is just one. So the age is 21, which is between 10 and 30. It's not my real age, but it works for now. So one row is returned back. Let's say there's another transaction which is happening in parallel, and it does this insert. So there's a transaction T1 and there's a T2 which is happening in parallel with it, and it does this insert. So insert into users value 3 and Bob and 27. So now you have a new value. So 3, Bob, and 27. And T1, it's doing a lot of processing. It does a lot of steps. May not be step 2, maybe some other step. It does this query again. So the same query which executed earlier in step 1 of T1 is executing in some future step of it. And now instead of getting one row back, which it got earlier, now it gets 2 rows back, because there's a new row which is also satisfied by this condition. This is what is called a phantom read. Phantom read is basically when I read it, the same transaction at 2 different points gets different number of rows from the query result. So here it's getting only 1 row when it was executing in step 1. Here it gets 2 rows because there's a new row inserted in that particular table. This is called phantom read. So phantom read is when I get new data when I try to execute the same query twice in the same transaction. So now we have looked at all the 3 different problems that happen in a transaction. So we looked at phantom reads is the last example which we looked at. We started with dirty read, non-repeatable read, and now we are looking at phantom reads. So how do we prevent them? The way we prevent them is by using something called isolation level. So in a transaction, you can specify something called an isolation level. So you can say, I want this kind of an isolation level. There's a performance impact in having a very high isolation level. We'll discuss that as well. But in the program, you say, I want this particular isolation level. And depending on the isolation level, you would have a few set of problems or not. We'll look at that. So the first isolation level we'll look at is called read uncommitted. So read uncommitted is the simplest of the isolation levels, and it's kind of the when I look at transaction management as a whole, probably it's not the best option. So read uncommitted means a transaction, when it tries to read something, it might get uncommitted data from other transaction. That basically means if there are two transactions T1 and T2 in parallel, and T1 is updating some value. Is the step 1 of T1 is updating some value, like let's say the name here or the age is updated from 21 to 23. If T2 is trying to get the value, let's say T1 is not yet completed, it's still running. When T2 tries to get the value, it gets the new value 23. So that's basically what read uncommitted is. So basically there is whether T1 is committed or not, it doesn't really matter. T2 gets the same value. So if T1 is completed execution, it would get T23, T2 would get 23. If T1 has not completed execution, even then T2 would get the new value 23, and that's basically called read uncommitted. So basically the database management system doesn't do anything about it. So if a transaction update, like whatever is in the database, whether it's committed, whether it's uncommitted, it doesn't really matter. It would just give that value back. So that's basically called read uncommitted. So in read uncommitted transaction isolation level, this is not solved. So this is not solved. Non-repeatable reads, dirty read itself is not solved. So the rest are not solved at all. A read committed. So read committed. The next one is read committed. So let's just say read committed is when only the committed data is read, allowed to be read. So what the database management system does is only if the transaction has committed the data, it would return it back. So let's say T1 is updating now to this particular thing to 25, and T2 is now trying to read this 25. So it would what the database does is it would do something called a log. So this particular thing, which I'm making it bold, you can treat it as a log. So T1 has updated the age to 25. T2 is now trying to reach 25, but this cell is logged. This cell is logged by T1. So what the database management system does is it waits until this particular transaction completes. So only when T1 completes, then the lock is released. So the lock is released. I show it by making it unbold, and now T2 can access the value. So this is now a committed value, and T2 can access it. Let's say T1 now is let's take a step back. T1 is now updating this to 25. T2 is trying to read it, but T1 has the lock, so it will not be able to. T2 has locks, so T1 has the lock, so T2 will not be able to read it. So it keeps waiting. T1 fails, and it reverts the value, and it completes execution. Now T2 gets the old value. Either way, whether the T1 fails or T1 succeeds, whatever value it has finally updated the column to, that is the value which T2 gets. This is what is called read committed. In read committed, we have something called write logs. So whenever a table, whenever a value is changed, then it's the entire row is logged. So whenever this 23 is changed, there is a lock, and the transaction holds the lock. T1 holds the lock to that particular row. Only when T1 completes execution, any other transaction would be able to read that particular row. This is called a write lock. So this is called a write lock. So once I write something to a row, I have the lock to it, and only when I complete execution, I mean all the steps are done, then the lock is released, and only then the other transactions can read it. In read committed, dirty reads are solved, so you'll never have dirty reads. However, you can have non-repeatable reads possible, because let's say when T1 starts executing, the when T1 starts executing, the value here is 23. So T1 is reading the value 23. So T1 gets the value 23. However, in between, T2 comes in and it updates this value to 27, let's say, and it also commits the change. So it comes the change, so the lock is released. Now T1 is trying to read that value again. So T1 is trying to read the value, it would get the new value 27. So in read committed, the non-repeatable read is not solved and phantom read is not solved also. So the next one, repeatable reads, is one where all these are solved. So in repeatable reads, both dirty reads are solved and non-repeatable read problems are solved. However, the phantom reads are not solved. How the repeatable reads works is by having something called a read lock. So let's say there's a transaction 1 and this transaction 1 is reading this value. So it's doing a select on this particular row. Then it gets a lock. So this transaction has a read lock on this particular thing. And this transaction 2 wants to do something on this. So I want to change something here. I can't do it because transaction 1 has a lock to it, has a read lock. So transaction 1 has a read lock on this particular row. So transaction 2, when it sees that, oh, this transaction 1 is having a read lock on this, so I can't do anything, I have to wait. So the transaction 2 cannot do the update on it. Transaction 1 then again reads it. So because transaction 2 has not been able to change it, the value is guaranteed to be same as whatever it was earlier. Here I got 27 and here also I would get 27. T2 is still waiting, and now T1 completed execution, it releases the lock, and T2 now gets the new value and it can do whatever it wants with it. So this is what is called repeatable read. So this isolation level repeatable read solves both the dirty read problem and the non-repeatable read problem. However, phantom read is not solved because still I can insert a new row and I would get different values. So the level which solves the phantom read problem is called serializable. When in a serializable scenario, what are created is a read lock, a write log, and something called a range log. So basically, when T1 executes this query, so T1 step 1 is executing a query, age between 10 and 30. So there is a range log which is created as well. So a range log is created. So between 10 and 30. So between 10 and 30, a range lock is created. So this lock is created. So any row which has age between 10 and 30, you cannot either read or so age between 10 and 30. So T1 has executed, it selected the rows from the table which have age between 10 and 30. As soon as that's done, a range lock is created. So any row between age 10 and 30, no changes allowed. So when T2 tries to execute this step, so it's now trying to insert into the user a new value, Bob, with a value 27. 27 is between 10 and 30. So what happens is the database will not allow this to complete. So it would not allow this to complete. It will keep this on hold. So it would not allow this. So it will not do this. So it will put it on hold because the new age value is 27 and it falls between the range lock. So what it waits for is to T1 to go to the next step. So T1 continues execution. T1 goes to the next step. It does the row because there's a range lock. It is guaranteed to get only one row back, and it continues execution. And then once it completes the execution, it would release this range lock, and only then the insert would happen. So only then the T2 would be able to insert a row into this particular table. So that's basically how the serializable isolation level works, and it solves the problem of phantom reads. So in serializable, all the different problems that are associated with transaction management are solved. So these are the three different levels which are related to four different isolation levels, and which solves the three different problems that are present in transaction management. So there you go. That's basically a summary of the entire transaction management. We looked at what are the problems with transaction management and then different isolation levels. We also looked at ACID properties. If you have any questions or queries, please leave a comment. Thanks for watching. Until next time, bye.